Hi, the title of today's talk is Generating Executable Specification from Formal Semantics of WebAssembly. This is kind of a continued talk that I gave. When was it? Yeah. So this is the timeline that I showed before. The upper top was our JavaScript work papers, and that in the middle, our communication with the TC39, and we are still writing some papers about it. But the thing is, the very first paper, she said, and the reviewer number 2 envisioned, like this is the right order to design and document languages. First the semantics, then the implementation and documentation, ideally generate from the semantics. So we believed that from the beginning, but we had only one paper back then. But now we have this experience, and now we are experimenting this idea with Wasm. And we'd like to try more languages. And today I'm going to just share our experiences with a little bit of technical details, and maybe ask more questions later. So again, Wasm. As you all know, for a feature to be standardized in Wasm, 4 key artifacts must be presented to the W3C Wasm community group, this group, a formal specification for the feature in the form of mathematical rules written in LaTeX. Here, you're going to have 4 artifacts with different languages, right? The second, a prose pseudocode description of the feature's behavior written in restructured text markup. I think some of you already used that. And then an implementation of the feature in the Wasm reference interpreter written in OCaml. And finally, a suite of unit tests for the feature written in an enriched version of the Wasm text format. So you should know all of this to add a feature, right? So people have been struggling with this procedure, and there are difficulties for Wasm spec authors. The lack of visual clarity when reading the raw source. I'm going to show you some example in a minute. And complicating code reviews and necessitating repeated lengthy builds, right? It takes time to build even. And absence of useful abstraction capabilities in Sphinx markup and in the available LaTeX subset. And those tools, Sphinx and MathJax, they have some limitations. And difficulty in interpreting LaTeX errors, right? And no protection against misuse of definitions. So these issues brought us to this, right? I already showed this to you during the time. And in this room, all those red boxes people are here, sitting here. So it's a collective work with many people, right? And among these, various efforts, our team has been working on this red box. So from this declarative DSL, we like to extract algorithmic version of it. We call that animation. We may use a different term later because it's a bit different from the term used in the other setting. And out of that, we are generating this prose specification in the interpreter automatically. So one at a time, this reviewer number 2 said, ideally from this semantics, we do better generate documentation. So that's what we've been doing, right? So let's see another example. So here, this is binary operator in the current specification written in this, whatever you call that, COBOL style, algorithmic style, you name it, right? This is in prose. And bottom, we have this nice mathematical LaTeX notation, right? So it looks nice, but in order to have this pretty version, you need to write this. So for the prose specification, you need to have this, all markup thingy, and the bottom to have that pretty operation semantics, you need to write LaTeX. So actually in the beginning, because we've done that, one of my students wanted to parse this and try that for a month, and like, not for us. So we were like, oh, there should be something better than this, right? So this is the one example DSL description that Andreas showed yesterday. So binary operator semantics in the DSL. Here's the rule name with this rule. And this is the left-hand side, arrow, right-hand side. And as he said yesterday, the premise is are below, right? But still, yeah, that's doable, and it looks pretty close to the operation semantics. But so, it's pretty tempting to use this notation than that later. If you have differences in later, that's not for people. So, but this one is really readable. And out of that, we can generate this PDF file. This is just the current version that you can just run it and get this version. Again, they're very similar. So far, so good. But the thing is, there are two if expressions or statements here. If the binary operator with the C1 and C2 is C, if that's epsilon, right? And they actually mean different things. So if we translate that to AL, that becomes like this. So this previous DSL notation now comes to this version. Here we have this assertion added that's from the validation phase, and pop, and then the first equality is now let binding. And the second equality is now really comparison of those two things. So that in order to identify that, we need some kind of data flow analysis. So then the prose description has a different phrases for the same if expression in the DSL. The first one is now again, let C be the result of this binary operator operation. And the second one is gonna say that if the result is epsilon, right? So we need to identify that. And we are writing a paper and we are planning to submit that to PLDI in a month. So the detail will be there. And here's one slide for what's happening. So again, this DSL has this left-hand side in pink, arrow, right-hand side in blue with some sequence of premises, right? And what we actually do with this, translation is translate this pink LHS to have some values on the stack, right? Pop, blah from the stack, and let them be whatever, give them names. And right-hand side is going to be at the end. After calculation, push the value to the stack and execute something. And in between, we have these premises about those, some side conditions and equalities and all that. So one example was that equality, it could be either real comparison or some let binding. And one interesting thing is that Dongjun found out that actually this identifying this, from premises to this algorithmic version is NP-hard, and I like that. And he proved it by reduction from a non-NP-hard problem, the Executable problem. So we have a simple proof about that, and a general solution is going to be NP-hard. So we intentionally proposed a simple and very straightforward solution for that. So again, there's no paper yet. We are writing it. Okay, so then the next thing is, again, the reviewer number 2 said, ideally, we'd better generate this implementation as well, right? And some people after my talk asked about this implementation, like, can you generate an interpreter as well from the DSL? So in a way, yes, I'm gonna tell you the details a bit later. So we automatically generate implementation. It's not like a direct interpreter of Wasm. I'm going to show that structure in a minute, but we generate some implementation, right? And by using that, we call that extracted Wasm semantics. By using that, we ran this official Wasm unit test on this machine. And on this machine, the extracted semantics passed all 23,778 tests. So that do not include SIMD instructions, and that takes like 21 seconds. Okay, then before showing the structure, why not existing approaches? Do we really need this new one? So you may have heard of the K framework, right? And actually there is an attempt by this runtime verification to mechanize the semantics of Wasm, like several years ago. And from several years ago, but and Jaehyun tried to do that. He was like, how are they different, their approach and our approach. And can we convert our DSL to K so that we can take advantage of K tooling, right? So he spent like 1 week or two and then conclude that it's not a doable job and that the K is not enough for us. And there are several reasons. There's no support for prose specification generation, yeah, of course. No support for conditional rewriting. It's all unconditional. And it supports associative list, but does not support this. It does not support associative list. It has some ordered, prefixed order. And we had this conjecture, so we had a private personal communication meeting with one developer of the K framework, and he confirmed that. So we were like, okay, we can write this in the paper. How about PL2Redux? So again, Jaehyun tried to compare this with PL2Redux, and again, there is some version of Wasm Redux, right? This one again is incomplete. It cannot even run some test of Wasm. And PL2Redux shares the same limitations with K. And this one, we are gonna also have some getting confirmation meeting from one of the developers, but we haven't done that yet with PL2Redux. Then how about ES Meta? ES Meta meaning our JavaScript work. So we showed you this JavaScript work, and let me tell you a little bit more detail about it. So the first paper, GStat, what it does is to take this ECMAScript language specification written in prose. We take that and red arrows meaning automatically generating artifacts. So from this spec, we automatically generate a parser and abstract algorithms written in the prose specification. And these functions are written in intermediate representation for language semantics. And we call that intermediate representation for ECMAScript, IRES, right? So there's yet another language to describe the language semantics, right? Then when we have this Java, and we call these two together, those generated parser and semantics, mechanized specification. That's what we have been referring to by mechanized specification. Then when you have a JavaScript program, you can pass that to this generated parser, right? And by using this given spec, so you can have multiple versions of the semantics. For a given spec, for a given program, we can analyze, we can interpret that JavaScript program using this IR interpreter. So in that sense, we are not having a direct interpreter of JavaScript, but we have an indirect meta-level interpreter for JavaScript. So let me repeat what I just said. Right? What you would like to have is some code, right, which it takes a JavaScript program, evaluates, and gets you a value. That's simple, right? We may be able to do that, but we didn't because, then we need to, that's a lot of more work. But when we have this intermediate representation for the language semantics, when we have an interpreter for that language, right, then we can take this JavaScript program as an input value to this interpreter, right? And this interpreter is gonna take this, spec, the semantics, and the program and give you a result. So that's the main idea. And based on this GSAT, we could have all the other work. Okay, then what are we doing with Wasm? It's a bit different. It's similar but different, right? Because the input was in GSAT, the spec in prose, but now in SpecTag, we call this project SpecTag, by the way. SpecTag, input is Wasm semantics in DSL, right? The single source of the truth in DSL. And when we take this semantics, again, we have our AL functions that represent the Wasm semantics, but that is automatically generated by that translation from DSL to AL that I showed you. That is NP-hard, right? Okay, so when we have these AL functions then that's going to be for different set of functions for different version of Wasm. You know that, right? Okay, then again, this time we didn't generate a parser automatically. We may be able to do that, but yeah, there is a parser already. So we are going to use that handwritten parser. So we are going to take Wasm program, and then ASD is going to be passed to AL interpreter. Then again, we can get the result. So this is the Wasm interpreter. Again, indirect meta-level interpreter. But as an end user, you just give a Wasm program and you can get a result. The inside you may not want to know, right? You can just get the result. Another present is from this AL functions, you can now get the spec as well. So that's the main difference. So after my talk, some people asked about like, wait, you did this with GSEP, but it's an inverse order. Yeah, you understood correctly, right? The different thing. And another thing is, another point is that even with GSEP, we'd like to have the other direction as well. Why? Because IL is better than English, right? That's one thing. And another thing is that in JavaScript, I heard Wasm is similar in a sense. Implementations come first, then the spec. And there are multiple versions of the implementations in different browsers. So one idea that Jihyuk has is like to get the implementations and get some prose suggestion and come up with this IR and then generate this prose specification. That's even wilder, right? But I don't want to go there. Right? He'd like to do that. And with this one, yes, question.
I have a mic.
Oh, yeah.
So my question is, the Wasm parser doesn't come from SpecTech. Is it a goal to come from SpecTech?
We can do that, but not a goal yet because there are other things to do. But if it's desirable, why not? What do you think?
Yes. So one thing I've been hacking on is extending this DSL with a way to define grammars as well. So in principle, you could generate a parser from that. I just don't know how interesting that is. I mean, that might be like a student project, perhaps.
Well, so there's research now on like generating correct binary parsers that have proofs of correctness from DSLs for that. And it's non-trivial to write a binary parser for Wasm, so that could be interesting, actually.
Why is it not trivial? If you have a BNF grammar.
Making a fast one, too.
Yeah, but we don't care about fast here.
Well, I mean, eventually we're going to generate the whole VM, right?
Oh,
Okay.
so we can discuss that later. Thank you. So, yeah, thanks for those follow-up questions. So now that we have this Wasm core semantics, what can we do? So we have now regular or irregular meetings with Amal, Ahmed, and Lucy about this component model with my students. And Ben also mentioned this benchmark creation, the micro-Prado, and Daniel, Ben, and some of my students are meeting weekly about this benchmark creation by using record, reduce, and replay approach. And test generation, I think this is the most interesting topic for many people here. And I had to convince my students to work on this, but now I don't need to. Thanks a lot. So back to JavaScript test generation. This was the diagram that I showed before, but there were some questions, so I'm going to revisit this one more time. When we have this mechanized specification, right, we can generate syntax-directed program generation for the pool of the seed programs, right? And then we can have some mutator. And how are we going to mutate the seed programs? By using coverage guided mutation. That's what the SE people call it. And we can add assertions and then generate lots of conformance tests. And we run these tests using multiple engines, then we can find some bugs, right? But this is not enough, as I said. So our recent work about the extension is what? So far, those conformance testing and test coverage are about programs, not about the language specification. So we do need something different. Why? Because in JavaScript, even addition is difficult and very complex. 1 plus 2, 1 plus string 2 is 12 in a string, and all those weird semantics. Another thing is that even for addition, you need to read many pages of the ECMAScript, right? What is that? Add expression is add expert plus mul expert. And the number one, call this helper function, eval string or non-binary expression. And then it's like addition this way, subtraction this way. And there are so many things to follow. So only usual test coverage in these algorithms are not enough.
I'm actually pretty sure that the entire JavaScript spec is in the transitive closure of these operations.
Oh, that's highly likely, right? So what we introduced as a new coverage is feature-sensitive coverage, because the data in the language specification is language feature. So it's not like only one algorithm name, but with this, which feature are we testing? Another thing is that it's not enough, so we are having this in a K version of that. It also has call path, so we can add more features to look at. So it was good to have all this, because we could find many errors. But the thing is, it explodes, right? There are a lot of test requirements. So our extended work on this topic is to selectively generate test requirements and efficiently find interesting tests and things like interesting bugs, things like that. And more important thing or good thing is that we do not need to change the implementation a lot. One more time, this mechanized spec gets in, and we have the seed synthesizer, right? Making seed programs and adding assertion, and this is the mutator. So here, from the seed program pool, we get something, and we mutate them, put it in, and make the cycle. And here, what are we gonna mutate, which and how? That's determined by this coverage criterion. We only change that coverage criterion, and that's it. And I conjecture that the coverage will be different for Wasm, for JavaScript, because the main reason that it was difficult for me to convince my students to work on this test generation for Wasm is they say, Wasm semantics is really simple. And currently, the official test data, official test for this Wasm, they are 100% coverage. Really? But still, there are going to be errors. And now we have some, reports and anecdotes about that, and people are interested in using this. So I'm happy to work on this with my students. The last bit about our research topic, that JSPI, again, Sam suggested this to me like a month ago, and I was like, oh, what's that? And now Francis came to me about JSPI and brief explanation about what we've done in this land about multilingual analysis. In the beginning, we had only analyzer for standalone JavaScript, simple core JavaScript, but it was just the beginning. We had to manually model the interaction between JavaScript and HTML DOM. Lots of work, manual modeling that behavior. We don't want to do that anymore. The second thing is that JavaScript and C libraries, they can interact. And for this one, there's API, nice API called Web API, which has this function name and parameter types, return type, and even some properties. So out of those specifications, we automatically model their behaviors. Of course, it cannot have, assignments or the impure behaviors, but it has some behaviors, right? And we can detect those errors. And this was a collaborated work with Samsung Electronics, and they were happy to have this because we could find like 88 bugs. And let me think. It was like the precision rate was more than 80%. So first positive were not that many. But anyway, so they were happy to have this. And after that, this one is with Oracle Labs in Australia. Because JavaScript is so dynamic, these simple not really simple, but only static analysis cannot find many errors. So this one is more like, this one is more like what? Our record reduce and replay approach for benchmark creation. It's a bit different, but what we've done here is to run some JavaScript code and observe the behavior of this opaque code in C or C++, and record some dynamic values and then abstract them. So that's what we mean by modeling opaque code automatically. So this is the last slide. So what we've done with this in the multilingual world is when we worked on this JavaScript analysis, the first one was hybrid world, meaning the interaction between JavaScript and Android Java. We've collaborated with this guy at IBM, and they have clients in the banking in New York, and they wanted to get detect bugs in this interaction. So that's the beginning of this. And then we realized like, oh, this static analysis is too expensive and we can have a type system for that. And then, oh, there are so many weird interaction between advertisement. So I don't use Android. There are many weird, vulnerable things can happen. And since then, we've changed our focus to Java and C interaction using this JNI analysis. Here again, we started with static analysis, and there are so many unspecified behaviors of JNI, so we could generate test data to find them. So these are lines of our research in this multilingual analysis. And I think maybe not the same technique, but similar approach can find some weird, unspecified, or undesirable behaviors between Wasm and the other languages. So thanks for listening. And I think there are so many interesting things that we can do together. Thank you.
We can take some questions.
Andreas.
So I would assume, and I want to know if you agree, that like test generation for WebAssembly would be simpler in various ways. One is it's typed, so you can have type-directed generation. The other is, so you mentioned you need seeds to generate tests, right? Can you just take the reduction rules as seeds in the Wasm case? Because they are kind of like very simple examples, right, that you might be able to compose.
Yeah, right. I mean, so yeah, you mean generating the seed programs more systematically. Yeah, we can do that. And we can even use those reduction rules like guideline and using them as like node coverage or,
Right.
Yeah. We can do that. Okay. Thanks. Mike?
You mentioned that the part where you take the was it the inference rules and you turn it into like the sort of if-else sort of executable stuff was NP hard and required some data flow analysis. I look forward to reading about the data flow analysis at some point. But about the NP hardness, I assume like even if this is an NP hard problem, the instances are small enough because there are only so many premises and things. Can you just like brute force it and do that?
Very good question, but I think Dongjun eager to answer the question.
Yes, first of all, that is true. So for most of the reduction rules, the premises are so small that actually brute forcing can work for most cases. What was the problematic part was that we had to also make premises of module semantics. Like for module semantics, there's really lots of premises. And making them into a prose, while doing that, that does not scale well. So that's the reason we had to come up with a better solution than doing the brute force.
So my question is similar. They're basically the optimal solution is NP hard, and so there's an approximation.
Yeah.
And the approximation is just like more prose.
Can you repeat, please?
So the optimal thing is like the shortest prose. Is that the thing that's NP hard?
Oh no, the correct prose itself, making it itself is NP hard.
Okay, so it's a binary problem.
Yeah.
Okay.